Good afternoon to everyone. Bonjour. First, I would like to introduce myself. My name is Umamaheswaran Arunachalam, working as an assistant professor in the Department of Mathematics at SASTRA University, Tanjavur. I heartily say thanks to the CIMPA, CIRM and ICTP and Professor Bernard Keller for giving this wonderful opportunity. In this visit, I started collaborating work with Professor Bernard Keller and Professor Yuang. Also, I would like to say thanks to the SASTRA University Honorable Vice Chancellor Professor Vaidya Subramanian sir and Swaminathan sir, Planning and Development, Umamaheswari Madam, Dean, and SASTRA community peoples, all community peoples for their strong support to this visit. Okay, so my research topic is my research area is algebra. Mainly homological algebra. Recently I started a cluster algebra with Professor Bernard Keller. Today I am going to give the talk Tate-Hochschild Homology and Cohomology of models. So I would like to start basic preliminaries of homological algebra. Before going Tate-Hochschild homology, we needed these things. So I would like to start with the basic concepts of homological algebra. First, introduction. So the homological algebra is the branch of mathematics that studies on general algebraic settings. It started to be studied in the most basic fundamental level in the beginning of 18th century of as a branch of topology, and in 1940s it became an independent subject and the studies of objects of X and Tor functors among others. So relative homological algebra was founded by Eilenberg and Moore. The concepts of covers and envelopes of modules have played an important role in the theory of modules and rings and gave a great impact on homological algebra. The notion of pre-covers and pre-envelopes were introduced in the early 80s by Enoch. He gave a general definition in terms of commutative diagrams of modules over arbitrary rings. So first I would like to start with the basic definitions. What is projective model? What is injective model? What is projective resolution? What is projective dimension? Injective resolution, injective dimension, these things. So projective model. Projective model over an algebra. So on a model, P is called projective if there exists an if for any epimorphism, F is mapping from M into N, and for any homomorphism gamma is mapping from P into N, then there exists gamma bar is mapping from P into M such that can I continue? Such that f of gamma bar is f of gamma bar is gamma. So in other words, that is home A of P comma dash is mapping from home A of P comma M into home A of P comma N is surjective. That is, the following diagram is commutative. So following diagram is commutative. So M into N is an epimorphism. So gamma, here F is mapping from M into N, gamma is for any homomorphism P into N, then there exists gamma bar such that this diagram is commutative. So example of projective models. Any ring over itself any ring over itself is a projective module. Any ring over itself is a projective A module. Suppose R is ring. Suppose R is ring, and for any epimorphism M into N, for any epimorphism, here R, we are taking gamma is mapping from R into N, F is mapping from M into N, define gamma is mapping from R into N such that gamma of R is R into gamma of 1. So we needed to prove that R is projective. So just I am taking for any arbitrary element in R. So gamma of R equal to R into gamma of 1. Gamma of 1, it is inside of N. So F is onto homomorphism, then there exists M belongs to M such that R into F of M. So F is the R homomorphism, then we can write it F into Rm. F into Rm. So Rm, actually from Rm we can make one map from R to M, gamma bar. So I am defining the gamma bar of R is R into M. So here F of gamma bar of R. So this implies that gamma is F of gamma bar. So R is projective. Any ring over itself is a projective module. This is example 1. And Z over P squared Z, Pz, Z over Pz is a projective module. Third one, Pz over P squared Z is not a projective module because it is not a projective module. Just we are considering this diagram Pz into Pz over P squared Z, Pz over P squared Z. This is identity map. So here I am taking Z over P squared Z. This is multiplicative map P star tends to 0. So I am considering this. Here I want to prove that Pz over P squared Z is not projective. But suppose it is projective, what will happen? Suppose Pz over P squared Z is projective R module. Now your R is Z over P squared Z. Projective R module. So that means then there exists gamma bar such that this diagram is commutative. So our P star is a multiplicative map. P star is P plus P squared Z. This is our map, multiplicative map. I am taking one element. T is for T belongs to Z, Pt. So Pt plus P squared Z. This is equal to identity of P squared Z. But we are assuming Pz over P squared Z is projective. That means this diagram is commutative. P star of which is equal to P star of gamma bar of Pt plus P squared Z. So this is P star is P plus P squared Z, into of gamma bar of, for this one we can write this, we can write it P plus P squared Z into T plus P squared Z, like that we can write it. So gamma bar is a R homomorphism, that's why we are taking this P plus P squared Z of P plus P squared Z, like that we can take it, of gamma bar of T plus P squared Z. We are multiplying these two, P squared plus p square z. This is 0 element into gamma bar of t plus p squared z. So this is actually 0. This is 0 element. There is p squared z. 0 into gamma bar p squared z. 0 of anything is 0. P squared. Here this is we are taking for any non-zero element. This is for any non-zero element, but we are getting 0. This is contradiction. So this is contradiction. So Pz over p squared z is not a projective module. P squared over Pz is not a projective module. So injective. So can I start again? Okay. So now I'm going to take injective module. What is injective module? Injective A module. On A module is called on injective. Is called on injective if for any monomorphism, that means 1-1 homomorphism. For any monomorphism f is mapping from M into N, and for any homomorphism so gamma is mapping from N into E, then there exists gamma bar is mapping from N into E such that the following diagram is commutative. Such that the following diagram is commutative. Zero into M into N. This is F. 1-1 homomorphism. Here gamma is mapping from M into E. So here gamma bar and this diagram is commutative. That is gamma bar of F. This is dual of projective model. In projective model we are taking for any epimorphism. In injective model we are taking for any monomorphism. So example of injective models. Examples. First one, Q is an injective Z model. That is injective Z model. We are writing like that, QZ. So second one, Q over Z is an injective model. Injective Z model. So next one, what is projective resolution? What is projective resolution? So on A model, M has a projective resolution. If there exists on exact sequence, but P dot the complex is Pn into P1 into P dot into M into 0. There exists an exact sequence of projective models. Here projective models such that for each pi is projective, such that for each pi is projective. So every module is an epimorphic image of a projective module. Every module is an epimorphic image of a projective module. By using this over arbitrary algebra, every module has a projective resolution. So we can see this, we will see this. I am taking an A module, M is an A module here. I am taking this one. Every module is an epimorphic image of a projective module. Here I am taking projective P naught. This is epsilon. So here this is kernel of epsilon. This is monomorphism here. Monomorphism. Here I am considering this model kernel of epsilon. This is every module is, again I am applying, every module is an epimorphic image of a projective module. Here I am taking P1. Here this place kernel of something, this one kernel of P1 into kernel of epsilon. So again I am considering this module. So this is epimorphic image of a projective module P2. This is again kernel of this one. So here this one, this is commutative. Again we are making mapping P2 to P1. This is commutative. This is commutative. So this resolution, this is called the projective resolution of M. So from this, over arbitrary algebra, every module has a projective resolution. Projective resolution. Next, injective resolution. So example for, before the example for projective resolution is 0 into Z into Z. Here M is multiplication map into Z over M Z into 0. M is an integer, Z over M is M Z. This is Z over Z. Any ring over itself is a projective model. Z over Z is a projective. Z over Z is a projective. This is projective resolution of Z over M Z. Projective resolution of. Next, what is injective resolution? Next, what is injective resolution? Next, what is injective resolution? So on R model or on A model, M has an injective resolution. Injective resolution if there exists an exact sequence of injective models. I am notationally I am taking complex E dot 0 into M into E naught into E1 and so on. This is injective resolution of M, where each EI is injective. So every module can be embedded on injective module by using this property over arbitrary algebra. Every module has an injective envelope. So over arbitrary algebra, every module has a projective resolution. Every module has an injective resolution. Projective resolution, it is left resolution. Injective resolution is right resolution. Next, I am going to define the homology and cohomology of models. First, I am going to define cohomology of models. And let M and N be an arbitrary. M and N be an arbitrary models. Arbitrary A models. So now I am considering the projective resolution of M. Now I am considering, because over arbitrary algebra every module has a projective resolution. By using this I can take projective resolution of M. Projective resolution of M. So now I am considering the complex P dot is P1 into, here I am taking maybe Pn into Pn minus 1 into P1 into P0 into m into 0. So now I am going to apply the contravariant functor Hom over A dash comma n. So I am taking this contravariant functor, we are applying this in the above projective resolution, we will get the right complex. Right complex. This is Hom over A P dot comma n is mapping from 0 to Hom over A m comma n into Hom over A P0 comma n Hom over A P1 comma n Hom over A P2 comma n and moving on Hom over A Pn comma n. So we are getting this complex. Here I am taking just this is epsilon d0 d1 d1 dn minus 2. So this is dn minus 1, this is dn. So if you are applying this functor here in the functions, here epsilon star. So epsilon star means Hom over A epsilon comma n. So for epsilon star, like that we have to take for other di's. So here d0 star. So this is d1 star. So here dn star. This is the dn minus 1 star. So from this complex we are going to define nth cohomology of m comma n notationally by using x to functor m comma n is kernel of dn star divided by image of dn minus 1 star. So this is nth cohomology of m comma n modules. So like that we can define the homology. By using tensor product we are going to define nth homology of m comma n. Here in this case we are taking m is right A module and n is left A module. So m is right A module. Here this is for homology. Tensor functor is always a covariant functor. Hom functor, sometimes from Hom functor we can take covariant functor, also contravariant functor. So m is here m is right A module, and n is left A module. So again I am considering the projective resolution, same projective resolution. So maybe I will mention it 1. So I am considering the projective resolution again. Here apply the covariant functor dash tensor n over A. Apply the covariant functor in the above resolution. We will get the complex. Hom A P dot complex P dot over A, and which is mapping from so Pn minus 1 Pn tensor n over A into Pn minus 1 tensor n over A. It is going like that. P1 tensor n over A, P0 tensor n over A tends to 0. This is actually this is covariant functor. That's what we are taking here. Pn to Pn minus 1 is mapping is dn minus 1. This place dn star. I am writing dn star. I am using in suffix because it is covariant functor. Here this place dn minus 1 star. So here dn minus 2 star. So this place here d1 star D1 star, this is, sorry, here D naught star, this is D1 star. Now we can define the homology of m comma n by using Tor functor. So A m comma n is, so nth term, just we consider nth term, this one, kernel of this one, image of this one, kernel of dn minus 1 star divided by image of dn star. This is nth homology of m comma n. Here this one is nth cohomology of m comma n. And now we are looking, so Tate-Hochschild homology and cohomology. So before that I would like to one more definition. What is Gorenstein projective? What is Gorenstein projective? So on A module m is called, on A module m is called Gorenstein projective. If there exists a complete resolution, if there exists a complete projective resolution, complete projective resolution, that is our complex P dot is Pd plus 1 into Pd into Pd minus 1 and so on. This is complete projective resolution of M. Complete projective resolution of M. Complete projective resolution of M. Otherwise, properly I would like to define this. So P1 into P0 into P0 into P1 into this is complete projective resolution of M such that if you are applying the contravariant functor home over A dash comma M dash comma P dash for any P dash for any projective module is exact. This contravariant functor is exact. If you are applying this sequence again, it will be exact for any projective module, for any projective A module, P dash is for any projective module P dash, and such that co-kernel or kernel of P0 into P1 is which is isomorphic to M. If it satisfies this condition, then M is called a Gorenstein. M is called a Gorenstein projective. M is called the Gorenstein projective. Next, what is Tate-Hochschild homology and cohomology? Over enveloping algebra, we are going to define our Tate-Hochschild homology and cohomology of modules. So in this case actually Tate-Hochschild homology and cohomology. Tate-Hochschild homology and cohomology. Here A is K algebra. A is an algebra over the field K. A is an algebra over the field K. So also, and assume that suppose A is Noetherian. A is Noetherian. A is Noetherian. So when A is D Gorenstein, suppose A is D Gorenstein. Suppose A is D Gorenstein if injective dimension of A is less than D and injective dimension of A is less than D. So what is injective dimension? Suppose in your injective resolution, if you have finite length, suppose d is a least positive integer, injective resolution, length of the injective resolution is d, then injective dimension of A less than d, we can define like that, otherwise it is infinity. So here we are taking d is finite, A is d Gorenstein, and what is Suzuki, dth Suzuki, again I have to tell about dth Suzuki of M. So every module has a projective resolution, so I am considering this one, PD minus 1 P1 P0 into M into 0. This is projective resolution of M. So kernel of this one, maybe I would like to mention it. FD. So kernel FD here. We can write like that from your projective resolution. This kernel D is dth Suzuki of M. Dth Suzuki of M. So now I am taking M. P is a projective module. This is F, kernel F. You can get the short exact sequence. This is first Suzuki. So first Suzuki, notationally we are writing omega 1 of M. First Suzuki, dth Suzuki, omega d of M. Like that we are taking, and then like that we are taking. So so omega d of M is Gorenstein projective. Omega d of M for each d is Gorenstein projective. X over A, xi over A, omega 1 of M, comma A equal to 0 for every I greater than 0. For every I greater than 0. Now we are consider the enveloping algebra. A power E is A tensor A opposite over A power E. So A tensor A opposite. Consider this enveloping algebra. And suppose A power E is d Gorenstein. Suppose A power E is d Gorenstein and Noetherian. D Gorenstein and Noetherian. So then D Gorenstein and Noetherian. So consider the suppose A power E is d Gorenstein and Noetherian. Consider the identity bimodule. Again, consider the identity bimodule. Consider the identity bimodule. A is like that. This is belongs to mod A power A. So then omega d over, so I am writing omega d over A power E of A is Gorenstein projective. Gorenstein projective over A power E Choose two-sided resolution. Now choose two-sided resolution. So now choose choose two-sided resolution. Two-sided resolution in the Frobenius category. In the Frobenius category, M over A power E of Gorenstein projective finitely generated A power E modules. That is Cohen-Macaulay finitely generated A power E modules. Gorenstein projective, which is equal to the Cohen-Macaulay model. Cohen-Macaulay finitely generated projective A power E module. A power E module. So your complex P naught is P d plus 2 into P d plus 1 into P d into P d minus 1 and so on. So here omega d of A, this is Gorenstein projective. Omega d of A is Gorenstein projective. Here's Cohen-Macaulay models. These are Cohen-Macaulay models, as well Gorenstein projective as well as Cohen-Macaulay. So this is complete projective resolution. This is complete projective resolution. Complete projective resolution. So here we are taking two-sided resolution in the Frobenius category. What is Frobenius category? Your Frobenius category is an exact category with enough projectives and enough injectives, where the class of projective models and injective models are coincide. Now we can define Tate-Hochschild homology and cohomology. Now we can define Tate-Hochschild define the Tate-Hochschild homology. Define the Tate-Hochschild homology. Define the Tate-Hochschild homology of A. Homology of A as HN SG of A is Hn of P dot tensor A over A power E over A power E. This is Tate-Hochschild homology of A. So here we are considering enveloping algebra A power E. A power E is actually A tensor A opposite. Suppose A power E is Noetherian and D Gorenstein. So consider the identity bimodule A, then omega d A power E, A is Gorenstein projective over A power E. Now we are choosing two-sided resolution in the Frobenius category of Gorenstein projective finitely generated A power E models. This is complete projective resolution. So from this we are getting this one. So we are the homology of P dot tensor A. This is Hochschild. We are calling it Hochschild homology of A. Tate-Hochschild homology of A. Also it is called singular Hochschild homology. Also called singular Hochschild homology. Also called singular Hochschild homology. So similarly we can define Tate-Hochschild cohomology. Similarly we define Tate-Hochschild cohomology. Tate-Hochschild cohomology is defined by this is singular Hochschild homology of A. Tate-Hochschild homology or singular Hochschild homology, cohomology here. This is here notation we are taking like that H power n home functor. We are applying home functor For homology, we are applying tensor product. Here we are taking home functor. Home a power e p dot comma a. So this is Tate-Hochschild cohomology. This is called the Tate-Hochschild homology. So our exercise. So I am giving one exercise problem. Okay, we can try this. I am giving, this is exercise. So compute this. Compute this for the dual. Compute this for the dual numbers. Dual numbers. A is k of e, divided by epsilon square. So next we are taking some notations. Here A is right Noetherian algebra. Mod A is set of all finitely generated right A modules. Set of all finitely generated right A modules. Right A modules. And CB of mod A. CB of mod A is bounded complexes of set of all bounded complexes of finitely generated right A modules. Finitely generated right A modules. And again proj of A. This is set of all finitely generated projective A modules. Finitely generated projective right A modules. Projective right A modules. Also CB of proj A is bounded complexes of set of all bounded complexes of finitely generated projective modules. Finitely generated projective modules. Next one. These are some notations. Then CB of proj A is a full subcategory of, this is CB of mod A is a full subcategory. Is a full subcategory. Is a full subcategory. And another notation, bounded DG category of mod A. This is actually DG means differential graded. DG means differential graded. Differential graded. DG category of bounded complexes. DG category of bounded complexes of finitely generated right A modules. Finitely generated right A modules. Finitely generated right A modules. Next one. So singularity of A. So the stable, next one, the stable derived category. The stable derived category. The stable derived category or singularity category of A. Singularity category of A. Singularity category of A is defined by the Verdier quotient. Is defined by defined by the Verdier quotient. Yes, G of A is bounded category of finitely generated models divided by perfect category of A. The bounded derived category, that is the bounded derived category, bounded derived category of finitely generated right A modules, finitely generated right A modules by the perfect derived category, derived category of A. That is the full subcategory of complexes quasi isomorphism to bounded complexes of finitely generated projective modules. So it was introduced by Bushfish is an unpublished manuscript in 1986 and rediscovered by Orlow in 2003. So it was introduced by in 1986, Bushfish in 1986, and rediscovered by Orlow in 2003 in his paper. So link between, next I am going to start with the link between Hochschild homology and cohomology. Link between Hochschild homology and cohomology. So this relation is useful for giving the relation between Tate-Hochschild homology and cohomology. So I start this lemma. Here A be an algebra over the field K. So we have an isomorphism. Dual of Hochschild homology of A. This is Hochschild homology, which is isomorphic to nth cohomology of A, dual of A. So dual of A means, dual of A is home of A, K over K. This is dual of A. So proof of this lemma. So proof of this lemma. Our nth cohomology of Hochschild cohomology of A, dual of A. This is actually by the definition we are taking nth homology of right derived functor of O A, dual of A over A power A. This is the, it is coming from the base, definition of Hochschild homology. So actually this is H power n or home A power E A, dual of A. I am taking this one A, K. So which is isomorphic to for n or home K A tensor A over A power E, K, which is isomorphic to this one. this one here, which is isomorphic to R of h power n, actually h n. Here cohomology, we are getting here homology. H n of A tensor A over A power E comma A. Sorry. So this is actually, so this, okay, this is h power n home k. Okay, this is fine. This is fine. So from this home k h n A tensor A over A power E comma A. So this is actually dual of Hochschild homology of A. So we proved this theorem. We proved this basic lemma. So next theorem, relation between Tate-Hochschild homology and cohomology. Next one, the relation between Tate-Hochschild homology and cohomology. So here we are going to prove the following theorem or lemma. Dual of Tate-Hochschild homology of A comma A, which is isomorphic to Tate-Hochschild homology of A comma dual of A. Proof. So assume that A and A, A power E, that is enveloping algebra, or Gorenstein. Choose a two-sided, as usual, choose a two-sided resolution. Two-sided resolution. P0 is complex. PD plus 1 into PD into PD minus 1. So here this one is omega, this is d of A over A power E. This is actually Gorenstein projective, where all the kernels are Gorenstein projective, or Gorenstein projective. So the nth Tate-Hochschild cohomology of A comma M. Nth Tate-Hochschild cohomology of A comma M is for n home of P dot comma M. Also Tate-Hochschild homology of A comma M is, by using tensor product we define Hn P dot tensor M over A power E. Now we are going to prove the lemma. So dual of, I am taking RHS, I am taking our LHS, dual of Tate-Hochschild homology of A comma A. So by the definition we are taking dual of Hn over a power e, and then h power n. This is d of hn. Here it is coming h power n, dual of p dot tensor a over a power e. This is actually home dual of this one, home p dot tensor a comma k over a power e. Again it is h power n home over a power e p dot comma home k a comma k. So this is equivalent to the nth Tate-Hochschild homology of a comma dual of a. So hence we proved our lemma. So we proved this, me and Bernard Keller, we proved this lemma. Next one, our main theorem. Next I will focus our main theorem. So we have proved the isomorphism between Tate-Hochschild homology and Hochschild homology of DG singularity of A for the cases p greater than or equal to 2 and p less than or equal to -1. For p greater than or equal to 2 and p less than or equal to -1, we have an agreement. We have an agreement. Tate-Hochschild homology of A, which is isomorphic to Hochschild homology of DG singularity of A. For any self-injective algebra, for any self-injective algebra A, for any self-injective algebra A. So there are two cases. First I am going to prove for p greater than or equal to 2 and case 2 p less than or equal to -1. Proof of the theorem, main theorem. Proof of our theorem, case 1 is p greater than or equal to 2. P greater than or equal to 2. Here I am using the Keller result, one result. The Keller in 1999 proved this one. So let A be a finite dimensional algebra. Let A be a finite dimensional basic algebra. Let A be a finite dimensional basic algebra. We know that for p greater than or equal to 2, we have an isomorphism. Hochschild homology of DG singularity of A, Hochschild homology of DG singularity of A, which is isomorphic to or equivalent to Hochschild homology p minus 1 to Hochschild homology of A. So we are going to use this for proving case 1. Suppose that A is self-injective. So our case A is self-injective. A is suppose we are taking suppose A is self-injective. We compute Tate-Hochschild homology of A. To compute Tate-Hochschild homology of A, we choose two-sided resolution of A. We choose two-sided resolution of A. We choose two-sided resolution of A. The complex P dot is P1 into P naught into I naught into I1 and so on. So in this complete resolution, left side we are taking projective resolution, right side we are taking injective resolution. Since A is self-injective, so set of projective models and injective models are coincide. That's what we are considering like that. So this is complete resolution of A. This is complete resolution of A. Degree here, this is actually degree -2, -1. Here it is 0, 1, it is going like that. So now Tate-Hochschild homology, P the Tate-Hochschild homology, then P the Tate-Hochschild homology of A is HP of P dot tensor A over A power E. So for every P belongs to EZ. This is basic definition. It is from basic definition we are writing like that. So which is isomorphic to HP minus 1 of, only we are taking left resolution, P1 into P naught, P1 into P naught tensor A over A power E for every P greater than or equal to 2. So this one is isomorphic to this one if P greater than or equal to 2. So by lemma, by our previous by this lemma or theorem, by this theorem, this is actually Hochschild homology of P minus 1 Hochschild homology of A. Here for every P greater than or equal to 2. This is actually Tate-Hochschild homology of DG singularity of A. DG singularity of A. So this is last one. It is coming from our theorem, our Keller theorem, since by theorem. Since by theorem. So this implies that, so we have proved Tate-Hochschild homology of A is isomorphic to HSP DG singularity of A for every P greater than or equal to 2. So case 1. Now remaining we have to show that for P less than or equal to -1. Then case 2, P less than or equal to -1. So in this case, let us again we are taking projective resolution of A. Let us consider the projective resolution of A. Let us consider the projective resolution of A is P dot P D into P1 into P naught into A into 0. This is projective resolution. So dual of P naught is an injective resolution of A. This is dual of A into dual of P dot into dual of P1. this is injective resolution of dual of A. So for dual of A, since A is self-injective, so see if M is, suppose if M is bimodule, then dual of M is also still a bimodule. This is a bimodule actually, still a bimodule via or such that AFB of X, AFB of X is f of BXA for all A comma B belongs to A, X belongs to for all A comma B X also, for all A comma B comma X belongs to A, F belongs to dual of A, dual of A. Dual of A. Next, since A is basic self-injective, since A is basic self-injective, we have on Nakayama automorphism, then we have on Nakayama automorphism, gamma is mapping from A to A such that dual of A, which is isomorphic to A gamma. So this is isomorphic to, which is isomorphic to A gamma. This is invertible, gamma inverse A. So this gamma is called the Nakayama automorphism. So where A dot X dot B is AX gamma of B for every A comma X comma B, A comma B belongs to A, for every A comma B belongs to A, so X belongs to A gamma, for every X belongs to A gamma. So like this we are taking our Nakayama automorphism. Suppose we have a projective bimodule. Suppose we have a projective bimodule. Suppose we have a projective bimodule E1 tensor E2A for idempotence E1 comma E2 belongs to A. So dual of A E1 tensor E2A is dual of E2A tensor dual of A E1. Like that we can get. Like that we have actually dual of so then dual of A E1 tensor E to A is dual of E to A tensor dual of A E1. So we have dual of A, which is isomorphic to A gamma. This is isomorphic to here gamma inverse A. We are going to use this D of A E1. D of A E1 is E1 dual of A. So E1 for dual of A we are taking A gamma. So like that dual of E to A is E1. sorry, dual of E to A is dual of A dot E2. This is isomorphic to gamma inverse A dot E2. So dual of A E1 tensor A to A is, which is isomorphic to gamma inverse A E2 tensor E1 A gamma, which is isomorphic to this one. So note that A E2 so here A E1 is a right A model, E to A is a left A model, but here we are taking A E2. So A E2 is actually E to A. This is actually home of E to A comma A over A. So for this notation space we are taking like that. And E1A is A E1. This is home A E1 comma A. So if P1 is a right projective module, A module, and P2 is left projective A module, so then dual of the dual of P1 tensor P2 is dual of P2 tensor dual of P1. So this is actually gamma inverse P2 swish tensor P1 swish gamma. So which is dual of P1 tensor P2, which is isomorphic to this one. And if P is any projective, so this implies for any projective model A, for any projective model P, we have dual of P is isomorphic to, or dual of P is gamma inverse P swish gamma as A bimodule, So now remember the projective resolution of A. Now remember the projective resolution of A. Remember the projective resolution of A, P1 into P0 into A into 0. This is P0. So dual of P0 is actually we dualize it, get on injective resolution. We dualize it, we get an injective resolution. Dual of P dot is 0 into dual of A into dual of P0 into dual of P1, and so on. Like that we are getting. So this is dual of A is actually isomorphic to A gamma. So this is isomorphic to gamma inverse P naught swish gamma. So this one is isomorphic to gamma inverse P1 swish gamma. Here we are getting this one. So we twist gamma on the right to get an injective resolution. We twist gamma on the right to get an injective resolution. To get an injective resolution, 0 into A into gamma inverse P naught swish, gamma inverse P1 swish, and so on. This is an injective resolution. So now we are applying. We apply the covariant factor A tensor dash over A power E. In the above resolution, we get we get the complex. We get the complex A tensor over A power E gamma inverse P naught swish into A tensor over A power E gamma inverse P1 swish. We are getting this complex. So actually for any projective model, for any projective model, for any projective A model, we have A tensor over A power E gamma inverse P naught swish, which is equivalent to the isomorphic to the A gamma tensor over A power E P naught swish by the following relation. By the following relation. So this is very important. So by the following relation, AXB tensor P X tensor gamma inverse B PA. So if and only if AX gamma of B, which is equal to the X tensor B PA. So from this relation, these two are isomorphism, these two are equal. So again we are taking this one, A tensor over A power E gamma inverse P naught switch is A gamma tensor over A power E and gamma. So this is actually, so this one is home of P comma this is here actually we are taking this for any projective model, not only P naught. Here we are taking for any projective model. So now we are applying this. We are applying our projective resolution. This one, this resolution, this. So this is actually home A power E P comma A gamma. So A tensor over A power E gamma inverse A swish, here P naught, not only P naught. For any projective model, it will satisfy this. It will satisfy this. We are applying. We are going to apply this for our proof. So if P less than or equal to, we have to prove. Now we are coming to the proof of our theorem. if p less than or equal to minus 1, or if p less than or equal to minus 1, or we can take minus p greater than or equal to 1. So minus p greater than or equal to 1. So then minus pth Tate-Hochschild homology of A, by the definition, first by the definition we are writing this, H minus p of p dot is complex projective resolution of A, tensor A over A power A. First we are taking by the definition, and then this is actually HP, this is equal to the HP dual of P dot complex P dot tensor over A power E. So this is actually HP, this is dual of A tensor over A power E dual of P dot, which is actually equivalent to the HP A gamma tensor P dot swish. So this is actually Tate-Hochschild cohomology of A gamma A gamma. This is Tate-Hochschild cohomology of A gamma. So this is coming from this one. So from this A gamma tensor over A power E, which is this is actually equivalent to this one. So if we are applying this here, we will get this. So we will get this. So A gamma is actually dual of A. Again I am writing this A gamma dual of A. This is actually what HP, right, derived functor of home A power E A comma home A comma K. So like that we can write it again, H power P R or this is equivalent to the home K, home of A tensor A over A power E comma K over K. So this is equivalent to this one, this is isomorphic to this one. So again we are taking this is dual of, this is actually what, dual of A tensor A over A power E, H power P or dual of A tensor A over A power E over A power E. So I am continuing here, this is I am continuing here. So this is actually equivalent to the dual of H power minus P or A tensor A over A power E. This is actually dual of HHP of A. This is H power minus P. Minus pth cohomology is equivalent to the pth homology. So again we are going to apply Keller result, Bernard Keller 1999, B Keller 1999, prove the following. Proved the following: H minus P of dg singularity of A, which is isomorphic to dual of Hp of A for every P greater than or equal to 1. Now we are applying this here. We are getting dual of Tate-Hochschild homology of A. This is isomorphic to actually this one. So this implies that H minus P Tate-Hochschild homology of A is isomorphic to minus Tate-Hochschild homology of dg singularity of A for every p greater than or equal to 1, for every p greater than or equal to 1, otherwise, or we can take every p less than or equal to, or every p less than or equal to minus 1, for like that we can take this, like that we can take this. This is case 2. So from case 1 and case 2 we have proved our main theorem. Still p equal to 0 and p equal to 1 we are working, still it is open, we are working on this, so hence we proved our theorem, So question 1, question, what about for p equal to 0 and p equal to 1? Still we are 2 cases. So and the next one, question number 2. Also we are interested in the open question of the relation between Tate-Hochschild homology of A Tate-Hochschild homology of A and Tate-Hochschild homology of dg singularity of A. Homology of dg singularity of A. So we have proved the main theorem. Next we are concentrating these questions. Again I would like to cover some normal results. So already we proved one lemma. From that lemma I will give one more question. So already we proved this lemma. Already we have proved this one. Dual of Tate-Hochschild homology of N. Tate-Hochschild homology of N A comma A, which is isomorphic to Tate-Hochschild homology of A comma dual of A. So already our question. Suppose A an algebra such that suppose A is an algebra. Such that A and A power E are right Noetherian. Then Tate-Hochschild homology of A, which is isomorphic to Tate-Hochschild homology of S, where S is dg singularity of A. So if it is true, then this implies that this implies that this implies that this implies that so dual of Tate-Hochschild homology of A, which is isomorphic to so this is isomorphic to A comma dual of A. So this is isomorphic to nth Hochschild homology of S comma dual of IS. Therefore, this is isomorphic to this one, this is isomorphic to this one if it is so therefore we study the question of whether we have an isomorphism, whether we have an isomorphism, Tate-Hochschild cohomology of A comma dual of A, which is isomorphic to nth Hochschild homology of S comma dual of IS. We are studying this question. Next is I would like to cover what is Serre functors. What is Serre functor? So before in Serre functors, suppose C is a K-linear home finite category. So what is home finite? So I will take now Serre functors. Serre functors. Suppose C is a K-linear. Suppose C is a K-linear home finite category. Home finite category. What is home finite? What is home finite? Your home finite is home set is A is a finite length finite length K module So then we call A is home finite. A home finite. Now we can give the definition of Serre functor. A Serre functor C, a Serre functor C is an autoequivalence. A Serre functor C is an autoequivalence. S is mapping from C to C, which is isomorphism, such that we have bifunctorial isomorphism. Bifunctorial isomorphisms. Dual of home of x comma y over c, which is isomorphic to home of y comma s x. Here s is referred where d is s of x. So this d we know already, we discussed it. D is dual of this one. So example of Serre functors. Next example of Serre functors. Example 1. Example of Serre functors. Suppose A is symmetric. Suppose A is symmetric finite dimensional algebra. Finite dimensional algebra, that is dual of A, which is isomorphic to A as on A bimodule. A bimodule. So example for this, example A is K of G, group ring. G is a finite group. Here G is a finite group. Here G is a finite group. So C is actually our C, we are taking C is proj A. If we are taking proj A, already we defined this notation. That means finitely generated, set of all finitely generated projective right A modules. Set of all finitely generated projective right A modules. Right A modules. Now dual of home P comma Q. Now then, so dual of home P comma Q is home A, Q comma P tensor dual of A, which is equal to isomorphic to this one. This is isomorphic to this one. So again, which is isomorphic to home Q comma P tensor A over A. So this is isomorphic to home A, Q comma P. So here P is SP. S is identity in C. So this is isomorphic to home A, Q comma SP, where S is identity in C. So identity in this is our Serre functor. So identity in C is a Serre functor. This is one example for Serre functor. And one more example. Example 2. Suppose A is finite dimensional basic self-injective algebra. Suppose A is finite dimensional basic self-injective algebra. Suppose A is finite dimensional basic self-injective algebra, that is dual of A, again which is isomorphic to A. So as a write A by module, as a write A module, as a write A module, as a write A module. As a write A module. Now we are taking Nakayama automorphism. Then so dual of A, which is isomorphic to gamma A over A as a bimodule for an automorphism, gamma is mapping from A to A. This is called a Nakayama automorphism up to unique inner automorphism. Up to unique inner automorphism. This automorphism is called a Nakayama automorphism. Then dual of Hom of P comma Q, so which is isomorphic to Hom Q comma P tensor dual of A over A. So this is again isomorphic to Hom A Q comma P tensor A, P tensor A gamma A. So this is which is isomorphic to Hom over A Q comma P gamma. So by here maybe this is gamma inverse here, gamma inverse. So here we are getting gamma P gamma. So this is actually what? Hom over A Q comma S P. S P, where here S is, here S is here. So our S is base of gamma is a Serre functor. This is an example for Serre functor. And I would like to stop it here. So our future problem is we are interested in open question of the relation between Tate-Hochschild homology of A and Tate-Hochschild homology of DG singularity of A. DG singularity of A. Today I am going to finish my lecture now. I would like to stop it here. Tomorrow we will continue.